The great scientific revolution of the 20th century are quantum mechanics and general relativity. Quantum mechanics changed how we see matter and energy, but it uses the old notions of space and time. General relativity changed how we see gravity, space, and time, but it uses the old notion of matter and energy. This leaves us with a description of the world that is beautiful, fragmentary, and internally inconsistent. We don't really know what space and times are anymore, because the deeper we look, the more troubling the world appears to be.
Let me take you on a journey through our ideas of time.
I'll show you the physical arguments and thought experiments that lead us to where we are today, and the new answers physicists are building regarding the question of time. Time is something we are all familiar with. Time is an evidence like the space we move in and the air that we breathe. Yet the second we stop to think about it, it becomes mysterious. There is a now, which is the present we are living in right now. There is a past that we remember, but that we can never access. There is a future that we worry about. We don't know if the past still exists and if the future is already written. All we can do is understand time a little better and hope that it will bring us answers. Long before I became a physicist, as I was still a struggling teenager, my Latin teacher challenged our conception of time and changed our teenage worlds. She explains that to us that we think of time as linear. Linear time is the idea that the past is gone forever and the future is yet to come. But, she said, most cultures see time as cyclical, not linear. Days, seasons, and lifetimes repeat themselves cyclically. Times of happiness follow time of suffering before times of happiness come again. And many great civilizations like the Hindus, the Chinese, or the Aztecs adopted this view of time. The Hindus beautifully describe the cycles as Kala Chakra, the wheel of time. And even the pre-Christian Greeks had a cyclical view of time and history. Yet a revolution was brewing in the Greek world. A few Greek thinkers started noticing that the cyclical nature of time couldn't explain what time is. So in a great tradition of the Greek world, they had heated debates on the topic of time. We know, for example, that the orator Antiphon believes that time doesn't exist, but that it is a concept to measure the world. The philosophers Parmenides and Zeno saw time as an illusion. And the most famous philosopher of all times, Plato, thought that time had a beginning and that it was going somewhere. Plato's idea remained marginal within the Greek world, but it reached the ears of the early Christians. And the church fathers were busy founding Christianity, and they loved Plato. They were building the Bible by gathering important texts and forming a canon that would be the foundation for the new religion. They realized that Plato's idea of a linear time let them build the Bible as a story. The world would start with God's creation of the universe, and it would end with the apocalypse and the return of God. In their view, God created the universe with a plan, and each event is a step along his plan. Success and failures, joys and sorrows are all part of God's plan for the world. This view of time as a progression of a story still infuses our thinking today. For example, the political beliefs that modernity is better come from this Christian view of time. So do the beliefs that we are heading towards a dystopia or a brighter future. Central thinkers feel that the future is already decided. They'll say that we live in a deterministic world and our free will is an illusion. This idea stems both of cyclical and linear time. Other thinkers see the future as more open and yet to be written. And the thing is, we cannot yet decide who is more correct, but we can say that they're all somewhat wrong because physics paint a very strange picture of time. We as humans have an intuition of time. We have senses that let us estimate the passage of time. We have a circadian cycle regulating our days and nights, and many of us have periods that are more or less aligned with the cycles of the moon. We grow and age as each year passes. But our perception is human. Children see a year as a very long time because it represents a large chunk of their life. Old people see a year as a short amount of time because they already lived several decades. It became important for humans to measure time so they could handle meetings and plan their days. So we have records dating back to all the way to Mesopotamian societies who were building sun and water clocks to measure time. These types of clocks are precise enough for planning the start and end of the workday and roughly estimating durations, but they are not precise enough to make precise calculations. Our need for precise measurements grew with the advent of sailing long distances. Ships would spend days and weeks without seeing land, and they had to estimate their position on the Earth. Since the world is almost a sphere, humans divided it vertically and horizontally with lines that we call latitude and longitude. People would calculate their position on the Earth and be able to find their position on a map. This matters if people are at sea and only see water and sky. Latitude is easy to measure. We can use the position of the sun and of specific stars at specific times of the day to know on which latitude we find ourselves. We can use the sextant, a simple tool that allows one to measure the angle between two objects. We can then compare the angle we found with a conversion table that tells us on which latitude we are. Longitude is much harder to challenge, and it took nearly 200 years to complete it. We can compute our longitudinal position if we know the time precisely, a bit like with latitude, but to do so we need an accurate clock. So the challenge became the invention of an accurate clock. This search lasted decades and even led to the discovery that light has a finite speed. Let me explain. The Danish astronomer Ole Rømer was building a universal clock. He figured that if we could count the eclipses of the moon Io around Jupiter, we could measure time. His measurements revealed that the length of the eclipses depended on the position of the Earth and of Jupiter. So he realized that the only explanation was that light had a speed, which he even estimated. So we owe him the first measurement of the speed of light. Alas, ships moved too much to measure the orbits of Io around Jupiter, so the solution of Ole Rømer didn't work. The challenge was eventually solved by Johnny Harrison. He invented several chronometers in the middle part of the 18th century that were precise enough to change the world of sailing. Today, our most precise clock is in the United States. It uses a vibration of strontium-87 to measure time. The atoms of strontium-87 tick 1 million billion times per second, or 10 to the power 15 times per second. This clock is used to calculate the effect of gravity on time and to study general relativity. But despite its great precision, it cannot tell us what time is. So let's look at what physicists think about time. Newton offered us a remarkable tool, the scientific method. He realized that we cannot trust our intuition. We can use what we see as facts to begin our reasoning, but conclusions based on our intuition will deceive us. I'll show you an example of this process with one of Newton's thought experiments. People believe that objects need a constant force to stay in motion. That is what we observe in our daily life. Things stop moving when we stop pushing them. But this meant that things that kept moving forever, like the sun and moon, somehow had something pushing them. And that seemed wrong. So Newton imagined a series of thought experiments to challenge this intuitive idea. He imagined a cart that someone would push on a road. If the person stops pushing the cart slows down and stops. And that's because the wheels have imperfections that resist motion, and the road is not perfectly smooth. But now let's imagine that the person makes the road smoother and installs wheels of higher quality. The cart will still slow down once we stop pushing, but it will go further. And now let's imagine a scenario where the wheels are perfect and the road is perfectly smooth. In this scenario, Newton thought, the cart would have no reason to slow down. It would roll forever. And that's how Newton offered us the remarkable law of inertia. And this leads us to Albert Einstein, time, and general relativity. Albert Einstein is someone who loved thought experiments. He by far preferred them to equations. So despite keeping math simple, he's someone who completely changed our way of seeing time by using clever ideas.
People at the time believed Newton, who wrote that absolute, true, and mathematical time, in and of itself and of its own nature, without reference to anything external, flows uniformly and by another name is called duration.
This view of time stuck for a very long time, so we all thought that time and space were the same for all of us. A galaxy very far away, the sun, and ourselves all share the same time. This belief posed a problem for Albert Einstein, who was thinking about the concept of the speed of light. 16 years old Einstein hated the rigid education method of his country of Germany. He was kicked out of school and ended up in a progressive school in Switzerland. This school put emphasis on independent thinking and visualization. The young Einstein started to wonder what it would be like to run alongside the light beam. He thought that he would see the light beam as stationary, standing next to him. But he also knew that light is made of electric and magnetic fields that obey Maxwell's equations. So he figured that the electric and the magnetic field would also hang next to him. This was impossible. For one, Maxwell clearly stated that the electromagnetic fields move at the speed of light, no exception allowed. An essential issue makes it impossible. We have the concept of relativity, says Galileo and Newton. The concept of relativity states that the laws of physics don't depend on how fast we are moving. Einstein should still see the same laws of physics when going at the speed of light than when being stationary. Albert Einstein spent over 10 years pondering over the issue. He tried every possible solution under the sun and failed. Eventually, he had to try something radical. What if Maxwell's equations applied everywhere, but the speed of light always remained the same? You can go as slow or as fast as you want, you will always see light going at the same velocity. He imagined a thought experiment with two observers on a light beam going at the speed of light. One person is standing on the side and not moving. The other person is on top of a train going really fast. Somehow, the person on the train should see the light going slower than the person outside the train. In this situation, Maxwell's equations applied to the same light beam would be different for each observer, and this violates the principle of relativity. Einstein's solution was a breakthrough in how we see the world. He realized that the two people experience time differently. Two events can happen at the same time for one observer, but at different time for the other observer, and they are both right, because time and simultaneity are relative. Einstein illustrated it with the following image. Two lightning bolts strike the ends of two trains. There is an observer on the side who is exactly next to the middle of the train when lightning strikes. She sees that the lightning struck both ends at the same time. But there is another observer standing on the middle of the train. Because the train is moving, the light coming from the back of the train has to travel more to reach her, so she sees that lightning struck the train in the front before it struck the train in the back. In this thought experiment, we can see that our notion of now is not clear. Something can be in the past for someone, in the future for someone else, and in the now for a third person. Albert Einstein developed general relativity by writing down equations solving this issue. He showed us that space, time, and velocity are related to each other. This leads us to describe time with two new notions. Einstein's idea is that time is relative and not absolute, and the idea that time only ever marches forward. The astrophysicist Arthur Eddington called this second idea the arrow of time. And the arrow of time is a beautiful way of saying that we have never seen information travel back in time. We can know what we ate for breakfast yesterday, but not what we will eat tomorrow. Time only flows in one direction. The time follows the arrow of time. There are two views that physicists adopt in regard of time. Someone like Neil deGrasse Tyson will explain that time is a variable, so we do not need to worry too much about its meaning. This view makes sense. After all, many phenomena are reversible in time, so it is reasonable to treat time as a variable in these cases. Forces like the force of gravity, electromagnetism, and the strong force do not depend on time. But the weak force is a notable exception. We can observe atomic decay, but not its reverse. Some physicists deeply reflect on what time means, and they focus on these events that are irreversible, like atomic decay. If an ice cube melts in a glass of water, it is gone forever and will never reappear. We can never unslice a tomato or unmix syrup on water. These phenomena are asymmetrical when it comes to time. This property of the world is called entropy in thermodynamics. Thermodynamics is the field of study of heat, temperature, and work exchanges. It's the field that first describes this irreversibility of nature. And in particular, the second law of thermodynamics explains that natural processes are irreversible. Processes can never change back because they change the world by creating entropy. Now, we usually describe entropy as a kind of disorder that increases over time, but that's not entirely exact. Entropy describes how the universe tends to homogenize energy differences over time. Places with more energy give energy to places with less energy until everything has evened out. And this is this process that creates entropy. Many modern physicists wonder if entropy is a true quantity that is making time pass. In their view, time is a quantity that comes out of the increase of entropy. If the world was completely still, without any exchange, time would freeze as well. We open this video by noting that we all have a sense of what is the present, the now. We saw that general relativity showed us that there is no universal now. Every point of the universe experiences its own space-time. Quantum physics brings a fascinating new angle to the idea of time. The word quantum comes from the word quanta, which are these tiny chunks of energy building the world. Many years ago, physicists realized that some of our observation of the world did not make sense. For example, electrons were orbiting atoms, but they weren't crashing into them. Worse, electrons seem to always have energies that were multiples of these quanta. You cannot give an electron any energy you want, you have only limited options, and the classical physics of the time couldn't explain why. These issues were solved with quantum physics, which Schrödinger's cat illustrates well. In the quantum world, things only get defined properties when they interact with something else, like the cat does with a human observing it. Without interactions, things do not have definite properties. This allows the physicist Laure to explain what is the now from the point of view of quantum physics. The now is when things that are indefinite in the quantum world become definite. The moment now, the present moment, is a transition from indefinite to definite. This leads us to the quantum physicist and author Carlo Rovelli. He takes the position that the building blocks of our world aren't particles or even fields, but they are quantum events. Our universe is built on events. This conclusion is not evident because we are like the fish swimming in water. Events and interactions on the small and large scale surround us. Yet Carlo Rovelli makes the ambitious claim that if we could know the position and the speed of all particles in the universe, we would no longer have entropy, and we would have no unraveling of time. This novel idea is called thermal time hypothesis, and it still needs to be verified. Now, if you'd like to dig deeper into the way physicists see the world, I'm a physicist, and I regularly make new videos on my channel. I recommend that you watch the one I made on Bell's theorem. It's a theorem that proves that our universe is quantum, and we will never be able to explain it with classical physics. I use a spinning wheel to visually explain the entanglement of two particles, even separated by very large distances. I love thought experiments, they are a brilliant way to think about the world, and that's why I love discussions that center on ideas and not just on math. So I hope I managed to expand your worldview a little bit, and I would love to see you again.